Okay, so where have we gotten to? We started with some very general discussions about n=1 compactifications, SU3 structure manifolds. We've done a bit of a diversion in terms of Calabi-Yao's and being able to bound geometry. How do you try and classify? How do you try and build? How do you extract features of interest? For this last lecture, I want to return to some of that n=1 geometry that is different than n=2 theories, where you have more than just a manifold. You also have to include other things in the background that specifies your string compactification. So for example, gauge fields in background, fluxes, branes, et cetera, orientifold planes. So the game today is we want to consider more n=1 geometry. And here by geometry, I don't mean, so not just X, for example, X6, a compactification manifold, but also instead things like gauge fields over it, which we can describe as certain bundles over X, branes, fluxes, et cetera. And to begin with, just to give an example of now what the complete geometry looks like and its effective theory, I'm going to focus on bundles for just a moment, because this is in the regime where I've been talking about heterotic string theory. This is in the perturbative regime, and it's where we can say a lot. I also want to highlight several sort of recent developments, both computational and more, abstract understanding, that have led to better computational control of these theories. So returning to that n=1 structure, in the case of the E8 cross E8 heterotic string, intendi, right, we're considering our solutions. Let's stick with Calabi-Yau for the moment, although we can move on to more general solutions in just a moment. But we have solutions of this type. And now, because we have gauge fields in the 10-dimensional theory, we also have to specify what are the gauge field vevs over the compact extra dimensions, right? So a question is, what is a mu on X6? In order to specify that, of course, we have to solve the equations of motion for the gauge fields, which I've been ignoring up to this point. So we talked in detail about solving the SU3 structure system, or considering, the Calabi-Yau case of Ricci-flat solutions. So we have to look at those spinor variations that we started with in the first day and ask, what does this imply? And in the case of gauge fields in real coordinates, you receive equations like this. This would be in real. And if we restrict to the heterotic context where we're going to look at SU3 structure solutions, all of these are complex. So we can rewrite this in the complex setting as the following set of coordinates. Sorry, following set of conditions, which is that the 0, 2, and 2, 0 parts of the field strength of our gauge fields over the Calabi-Yau background must be 0. And that the 1, 1 part contracted with the metric must vanish. This system of equations is known as the Hermitian Yang-Mills equations. And the form of the equations is actually unchanged going from the SU3 structure to Calabi-Yau case. So the form of these equations looks the same. The difference, of course, would be that this would be the Calabi-Yau metric in the case of the Calabi-Yau geometry, and for a more general non-Ricci-flat metric, it would be a different metric here. Okay, just to emphasize, we needed to solve the equations of motion for the base manifold. And remember, even in the Calabi-Yau case, we have an existence theorem for a Calabi-Yau metric due to Yau, but we don't explicitly know the metric. So now you have a hard problem in differential geometry. You need to solve this equation for some gauge fields with a metric that you don't know. So that also is a difficult problem. Fortunately, there is a alternative packaging of this differential geometric system in terms of algebraic geometry. Although, as frequently happens, there is a conservation of misery in the sense that you have a hard problem in differential geometry, which can frequently be a hard problem in algebraic geometry as well. But let me say that this is one-to-one with properties in algebraic geometry. Specifically, this is due, what I'm going to mention, a theorem due to Donaldson, Uhlenbeck, and Yau. And Yau. And in terms of brackets, there was an Uhlenbeck-Yau paper and a Donaldson paper on this, so that is the division there. So what did they show? Well, the first part is easy. this doesn't require any demonstration really. This condition from your equations of motion is simply the statement that your vector bundle V over X is, quote, holomorphic. So this will be true whenever the transition functions of that bundle, as you move patch to patch on the manifold, are functions of your holomorphic coordinates only, not Z and Z bar. Okay. So this basically means that your bundle is playing nicely with the complex structure of its base. It's behaving as a nice holomorphic object as you move from patch to patch. So this part, pretty easy. This is the part that requires algebraic geometry. The condition, the metric-dependent condition that I mentioned that's tricky on the 1-1 part of the field strength, this is due to this theorem of Donaldson-Uhlenbeck-Yau, one-to-one with the algebraic geometric notion that the vector bundle, so V is slope, so-called polystable. I'm not going to get into details of what this property is. This has an algebraic geometric interpretation of certain subsheaf structure in the bundle that is, in principle, computable, though also frequently hard. Fortunately, for many classes of constructions of bundles, this is actually tractable. So I'll say hard but doable. Hard but possible. And similarly to the result of Yau's theorem, in which you know there's a Calabi-Yau metric, but you don't explicitly write it down, once you've checked the algebraic geometric properties of slope stability, you know that a connection exists that satisfies these equations, but you don't explicitly know that connection. So it's not constructive. Okay. So, good. So now, before I get into what the effective physics will look like, let me just very briefly, since I spent a bunch of time talking about how you might try and classify and bound the possible base manifolds, let's just talk about gauge field configurations over those compact directions for a moment and ask what is known. So one question you can ask is, can we bound topology of these gauge field configurations, these bundles? And the answer is yes, there's actually quite a lot we can say there. So what is the relevant topology that you want to understand for these vector bundles? The Chern classes, and remember these are traces of powers of the field strength. So first Chern class, trace of F, C2 of V, which is trace F wedge F, or Chern 2, C2 versus Chern 2, but we'll ignore that for a second. And the third Chern class. So Chern classes go up to the dimensionality of the underlying manifold as a complex manifold. That's 3 dimensions here. So 3 independent Chern classes. And you can ask, what do I understand from the heterotic theory about that data? First, C1 of V is actually 0 for any gauge group that can be embedded into E8. So if I have a gauge symmetry G, gauge group associated to V, and G embeds in E8, because E8 is traceless, this actually tells you that C1 of V must be 0. This is actually a good thing, because you need that C1 of V is equal to 0 mod 2 due to the Stiefel-Whitney classes in order to admit spinors on the underlying geometry, so to have a spin structure in the presence of the bundle and the Calabi-Yau. So the fact that it's strictly 0 does indeed satisfy spinors. We're good there. So the first Chern class is fixed to be 0. The second Chern class is actually bounded by the non-trivial Bianchi identity in terms of the heterotic 3 form that I introduced in my first lecture. So recall this condition that DH goes like trace F wedge F minus trace R wedge R. This has an integrability condition associated with it, which says that C2 of your holomorphic vector bundle has to be equal to C2 of the holomorphic tangent bundle in the purely perturbative theory. And if you're willing to include non-perturbative effects, for example, in the weakly coupled string NS5 branes, or in the heterotic M theory picture M5 branes, that can be modified to include a class C, where this is an effective curve that could support, say, NS5 branes. Okay. What that means, because this curve is effective, this is effectively a positivity bound that tells you that the second Chern class of your bundle can only get so big, it's going to be bounded by the second Chern class of your manifold. So if you pick a base manifold, then your second Chern class doesn't have very far to go in terms of topology. And for the third Chern class, This, interestingly, has a strong physical significance in the heterotic theory. This is also for bundles of this type. This is the index of the associated bundle, and this tells you the number of generations minus number of anti-generations in the effective Yang-Mills theory coupled to gravity. So this is the chiral index that tells you about the chiral asymmetry of the theory. For example, the standard model having 3 families but no anti-families. This asymmetry is measured by the third Chern class of your bundle. There's also a very nice result which says that if your bundle is slope stable and you can constrain C1 and C2, then there are a finite number of possible values for any bundle V that satisfies your equation of motion for C3. So there is a theorem due to Maruyama and Langer, which says if C1 and C2 of V are fixed, then there exists a finite number of possible C3s. Which is interesting in the sense that it says just in terms of the underlying Yang-Mills theory, it is not possible to have a theory, for example, with an infinite number of generations, right? The number of generations in your theory is intrinsically bounded in any perturbative heterotic theory due to the supersymmetry conditions. So underlying this, we can take away from these 3 results that they're going to be, for a given x, finite topologies for any V. So if I consider any possible gauge field over it, there is a bounded set of things that I must consider for the gauge fields. Now you could ask, do I know all of what those gauge fields are? And the answer is, no, I don't. Classifications of the moduli space of these semi-stable sheaves over Calabi-Yau manifolds is a very rich, open question in geometry. For certain examples, certain special topologies, we can describe those moduli spaces very explicitly, but in general, we don't know how to build all of them. So much like in the Calabi-Yau case, we still have the issue of, can you explore systematically everything that's possible? Before moving further with that, though, let me now say, given a background geometry and some gauge field that does all these nice things, is slope stable, satisfies the Hermitian Yang-Mills equations, what is the rough structure of the effective theory that results from that? So let's try and perform the string compactification if we are given. Now, again, I'm going to consider the perturbative theory for a moment, no fibranes, just to make things simple. Let's begin with some manifold X and a vector bundle over it, both of which satisfying our equations of motion. We actually have a pair of V's because we have 2 Yates factors in the 10D theory. We have V for I equals 1 and 2, such that their structure groups G embed inside E8, 1 for each E8 factor in the 10-dimensional theory. As we said, these are solving, so these guys are slope stable. They satisfy our equations of motion. And then the presence of these vector bundles in the definition of the background means that those gauge field vevs over the Calabi-Yau will break some of the E8 symmetry and leave only a remainder of that present unbroken in the 4D theory. So the 4D, n equals 1 EFT, is going to be some Yang-Mills plus Sugra in 4 dimensions. We can ask what it is. So what properties of this Yang-Mills theory can we find? V is going to break E8. And in particular, if we consider a maximal subgroup, G cross H, inside E8, if this is your bundle V, then the unbroken 4D gauge symmetry will be the commutant of G inside E8. So this will result in a 4D gut group H. So for a classic set of examples, if you were to take G, the structure group of your bundle, to be SU3, the commutant of SU3 inside E8 is E6. If G were SU4, for example, this would result in an SO10 theory. And SU5, there's a maximal SU5 subgroup of E8, will lead to an SU5 gut in 4 dimensions. Depending on what you want to do with this theory, at this stage there are many options. So in the last n years, where n is many, people have considered lots of particle physics model building. Why is that useful to do in the heterotic context? Because, of course, having nice big gut groups, you can then consider ways to break them down to, for example, standard model symmetry. You can ask, can I find SU3, SU2, U1 in here? Can I write down matter spectrum that's consistent with what we could see in nature? And you can push that actually really far in the heterotic context, and many things work very nicely just at the level of particle physics, in that you have nice ways of breaking these gut groups. It is possible to write down spectra that look at least like the supersymmetric MSSM, if that's the kind of thing you're interested in. So many features can be written here, but in order to fully specify the vacuum of the theory, you have to really control this effective theory to a way that has not historically been possible. So if you want to sort of point of principle, say, can I get pheno-looking things out of these solutions? The answer is going to be yes. But to really control them, there's still work to be done. So I'm not going to deep dive in that direction hugely at the moment, but let me emphasize a little bit about the particle spectrum. So you can ask what matter is in the theory, what charge matter, and of course, all of the matter that is going to be charged under these gauge groups, in 10 dimensions in the E8 cross E8 Lagrangian, the only thing that appears is the gauge field. So you have no charge matter, charge under E8 in the 10-dimensional theory. So all matter in the 4-dimensional theory has to come from the adjoint of E8. So the question here will be, what is the 248-dimensional adjoint of E8 decompose into in terms of this solution R13 cross X? Also, in terms of the choice of gauge field vevs over the Calabi-Yau versus over the 4-dimensional space. So for example, let me just pick a choice. Let's look at the SU5. Erase some more here so I don't confuse you. SU5 subgroup of E8. Then in this case, the 248 has the following decomposition in terms of that product group structure. So here, the numbers in brackets are representations of these two product SU5s. The reason that I mention this is extremely restrictive in the perturbative theory, because if, for example, you choose an SU5 gauge bundle in the Calabi-Yau, you get some SU5 gut in 4 dimensions. The representation content now of that 4-dimensional theory is entirely fixed in terms of what you can get by this decomposition. So for example, notice that there is no adjoint Higgs in the SU5, right? So a lot of like the standard gut breaking that you would do from just a 4D theory breaking does not arise in this case. The only adjoint here is actually the gauge field, valued thing is the gauge field. Now, this is what group theoretically can arise, but now you have to ask how much actually does arise. And the charge matter is counted multiplicity-wise by vector bundle valued cohomology groups over the Calabi-Yau. So notationally, what do I mean by this? These are things like, for example, in the vector bundle, you want to ask how many closed but not exact bundle valued 1 forms are there? I'll explain where this is coming from in just a moment, but let me just write the result. The number of 5s would be H1 of wedge 2 V dual. The number of 5 bars, H1 wedge 2V. So these are certain representations of gauge fields over the Calabi-Yau. Will count for you the multiplicity of the 4D fields. Let me just explain very roughly what's happening with that. If you consider a 10-dimensional gauge field, right, where is this matter coming from? The 10-dimensional gauge field will have some 10-dimensional index on it. When that index is pointing over the 4 dimensions, that's going to be a gauge field in 4 dimensions, right? When that's pointing over the Calabi-Yau directions, let's call that mu, that appears like a field in terms, scalar field in the 4D theory. So the multiplicity of all of this is being counted by an expansion of the gauge field. Let's write the gauge field components over the Calabi-Yau. So I'm actually using a bar here to denote the Calabi-Yau direction. this will look like some background gauge field plus a fluctuation around it. And now let me write it this way. It will have a decomposition of this form where this is going to be your 4D field, and this is a harmonic form over the Calabi-Yau. Harmonic bundle-valued form. So this satisfies dV and star, dV equals 0. That's a gauge covariant derivative. So an expansion of fluctuations of the gauge field is giving you 4D fields expanded in a basis of harmonic forms supported over the Calabi-Yau. So the question of how many 4D gauge fields do I have is really determined by harmonic forms on the base manifold, and then you have to actually just calculate what those are. So you could write down some bundle and say, oh, I could have, a 5 and a 10 rep in terms of the SU5 theory, but you go away and calculate it for that Calabi-Yau, and you don't really, because there are no harmonic forms. So that is the calculation that you have to do. Also should mention what happens to the singlets in the theory. So these are things uncharged by the 4D gauge group. Of course, we have the degrees of freedom that are coming from the metric reduction. So this is our familiar Calabi-Yau moduli, if I'm in that case, the dilaton from 10 dimensions, and we also have degrees of freedom that come from fluctuations of the gauge field that do not change your equations of motion. These are H1 over X of the traceless endomorphisms of your vector bundle. So there are fluctuations of the gauge field that don't change anything. Those are moduli changes of the connection that don't change the equations of motion, just like these are changes of the metric that still satisfy Ricci flatness. Importantly, I have not written that the number of singlets is a sum of these degrees of freedom. Because an important thing that happens in the n=1 context, and we'll return to this in just a few minutes, is that the moduli space really is different than in the case of n=2 theories, in that, as we'll see, the degrees of freedom from the gauge bundle and the metric are not independent. You don't get a nice product structure, you don't get a nice summation of these degrees of freedom necessarily. They can really talk to each other in non-trivial ways. And if you're hunting for something like a generalization of mirror symmetry to this n=1 context, this bigger moduli space that includes all those degrees of freedom is the thing that you must consider. So we'll return to that shortly. What else can we say about the effective physics? This will have, the form of this effective physics will be determined because we have n=1 supersymmetry. The potential can be written in terms of D and F terms. We have a superpotential in the n=1 theory. Let me not write all the details of that, but just schematically, if you wanted to consider, because of this decomposition right here, if you wanted to consider, for example, trilinear terms in your matter fields in the potential, in the superpotential, in fact. So imagine that you were interested in terms delta Cj, delta Ck, k, ijk in the 4D theory. How would those be computed? Because of this expansion, if you dimensionally reduce from the 10D theory, the number that you would get in terms of an overall coefficient of something like this, so this, what I've called kappa ijk here, would actually be computed as an integral of something like, I'm going to get my indices wrong here, but 3, let me just schematically write it, all of this on X. So you're going to have a triple product in terms of these V's of a computation of the wedge product of 3 bundle-valued 1 forms. So maybe a better way to write this is, VA, VB, VC, integrated over the Calabi-Yau. So now the coefficients in all the potential, all of these are in principle moduli dependent. They depend on the gauge field and the metric and background, but there's some explicit enough integral that you could perform to actually compute all the coefficients in the potential of mass terms, trilinear terms, and so on. These terms that I've highlighted here, these are part of the superpotential, and these are known as the holomorphic Yukawa couplings. And these, among other things, in terms of the underlying particle physics, are going to tell you about particle masses and interactions at the end of the day. So for example, if you're breaking that SU5 down to something like the standard model, and you have pairings with a Higgs this will give you the quark masses in an underlying theory. Formally, in terms of algebraic geometry, this triple product in terms of bundle-valued forms over the Calabi-Yau also is known as a Yaneda pairing. And there are very nice tools in computational algebraic geometry to calculate it. These are mappings, for example, for one type of matter, the 5s or 10s in this case. Says that there's natural triple pairings between elements of bundle-valued cohomologies that form a map into C. And these, the only point I want to convey at this stage is these can, in principle, be computed quite explicitly. They are functions of the moduli. So now you have the problem, let's say you're computing quark masses and you want to say, are they, quote, right? From, there's many levels of that question because we don't have a full vacuum specified yet. But now this gives you a question about, for what regions of moduli space can you have a realistic mass? You can start, asking more detailed questions. Yeah.
This triple intersection number that you wrote, it's like giving us the coupling, this coefficient that. But will it be dependent on the size of the cycle, like Kähler moduli or something?
Absolutely, and it's not an integer in the n equals 1 case. So
okay.
In n equals 2, a lot of these triple intersection numbers are, things like you can use mirror symmetry to compute, they end up being integers. In general, these are just numbers.
Okay.
And they are numbers that are functions of all the moduli in the theory.
Even complex
Sorry,
structure moduli?
Maybe I didn't understand your question properly. No, they're not a function of the Kähler moduli. There are actually results about that in terms of the decomposition of how axion monodromy can transform in terms of the superpotential. These particular terms appear in the 4D superpotential, and they are all holomorphic. So these are functions of the complex structure and bundle moduli only, not the Kähler moduli in this case. Kähler moduli appear in other parts of the theory in, for example, the normalization of these terms. So the matter field Kähler potential. But
okay. These Yukawa couplings, you mean?
Correct.
They Kähler moduli will appear there, or
they will not appear in the.
Okay.
So in all of this, no Kähler moduli appear.
Okay.
But in the Kähler metric on the matter fields, so to properly normalize those fields, that is a Kähler moduli dependent thing. Okay, so that's actually, that question is a good segue into what we want to do next. So historically, again, people have developed lots of nice tools for actually computing the structure of these potentials very explicitly, even as functions of the moduli. I alluded to this before, but one of the reasons people were very interested in this Calabi-Yau substructure is that if you have, for example, fibrations, these products take very simple forms. You can sort of decompose all of this structure in the potential in terms of the geometric ingredients of a fiber and a base. There's lots of nice things you can do. But a really key point is that the overall normalization of those fields does include more information that is harder to achieve. So one of the things that's nice about this is because, and I'll emphasize this, this is a holomorphic quantity. It's really depending on the complex geometry of the underlying manifold bundle pair. So it's interested in the complex structure of the base, the moduli of the holomorphic connection. Those are all complex degrees of freedom. The Kähler degrees of freedom don't appear in this product directly, but they do appear in the matter field Kähler metric. So to compute this, again, the same notation roughly that I have been using. Here's the same harmonic forms that we were expanding all our matter fields in terms of a basis of over the Calabi-Yau, but notice this unfortunate Hodge star. Okay? This is a manifestly Calabi-Yau metric dependent quantity. And this is not holomorphic. There is, this is a, bundle valued Hodge star is what I should emphasize. This is not a holomorphic quantity. It depends on the metric, and it is essentially unknown analytically. So very little was understood about how to compute this. This is a really big limitation in terms of asking questions about the full vacuum structure, moduli stabilization, trying to model build with these particles, because you really can't control the full theory. So one of these questions of like, hey, these questions have been interesting in string compactifications for 30 years, why haven't people made progress, is that you get to a certain stage, and then you just can't solve the equations. Because you say, I need this information about the theory, for example, this, and I just don't have it. So how do I push forward? And for that, there has been some pretty substantial progress in recent years, and I want to do a very brief detour for 10 minutes or so to illustrate some of that progress, which has involved techniques from machine learning. As we all know, machine learning is everywhere these days in many things. If you are a scientist and you have reviewed any grant proposal in the last 5 years, everybody has the statement like, let me just dump some machine learning on whatever problem it is that at hand, and that's going to be great. I personally, when I sort of started using these as tools, was a little bit skeptical as to whether machine learning algorithms were going to provide really new tools for solving, for example, complex differential equations and high order and many variables. The kinds of problems I was interested in, is this really going to be a regime change in terms of how we can compute things, or is this just buzz? I have since, over a number of years, been very, very impressed, actually, with what neural networks can perform in this context. And I'm going to show you an application of machine learning that's a little different than many things that you may have seen before. So many applications of machine learning involve training neural networks to known data sets of things, right? You give ChatGPT the internet, it does all its training, now it gives you back all the answers to all the things, right? You have a known data set of, learn these pictures of faces of beautiful actresses, now produce, the pictures of humans that, get generated by Midjourney and all these things. There you involve a data set that you train on, and then you produce an outcome. Obviously, in the case that I'm going to talk about, we don't know any Calabi-Yau metrics, so you don't have a data set to train a neural network on. So what I'm going to talk about is an application of machine learning that's referred to sometimes as semi-supervised learning or even direct learning, where we're really going to just use neural networks as a tool to try and solve complicated PDEs. And the question is, how does this perform versus other numeric PDE solving technology? So with that in background, let me give you the 2-second machine learning overview or aside here. So as I hope most people are familiar with, when people talk about machine learning, underlying this is the notion of neural networks. And sometimes these are referred to as a black box, but I think that's kind of misleading because these are actually extremely explicit functions that you can just write down. So neural networks are built by concatenating two things, some affine transformations. For example, z mu, simple linear function, and element-wise nonlinear functions. So let's swing this one up here. Z mu goes to sigma of z mu. So what does this look like? This ends up looking like these nice graphs that everybody sees in many places in the literature these days. I'm just going to do a simple example where you have an input space that's denoted by a set of nodes, and then I'm going to do a very simple toy here. Let's do the following. So here I'm defining a concatenation of two extremely simple things. I'm defining a two-dimensional output space that's going to lead to input space that's going to lead to a one-dimensional output space. And in such a case, the process that I just described here would look like the following. It would look like taking an input, z1, z2, and then performing this nested concatenation of things. Sorry. Hopefully you'll get the idea without me writing this all out. plus B12. Okay, so why am I bothering to write out a simple toy example like this? You have an input space, you have an output space. Here's some one-dimensional output from my two-dimensional input. In this case, the nonlinear function I've chosen is a tanh, and now I've nested, composed these linear mappings with nonlinear mappings, and out you come. The layers here are the intermediate step. So here I've written a very simple neural network with a single layer. As you've probably seen from many of these diagrams, these layers can be very large. So you can perform this concatenation many, many times, tens, thousands, millions of times, and produce a very deep array of nesting here. That's sometimes the number of layers that you're put on is referred to as deep learning, machine learning. So when you have many, many layers in here. And so this is some particular function that you write down. A great question is, who cares and why are we doing this? And the answer to that, in my view, is very much encoded by an old mathematical result, which is due to Sabenko, Leshno, and Pincus, who proved that this operation, given sufficiently many layers of affine transformations plus nonlinear activation here, that in this context, neural networks are universal approximators. Just like Taylor or Fourier series, you can approximate literally any function by doing the type of steps that I have taken. They're not constructive in terms of how many layers you need or what structure you need for that network, but theoretically you can approximate anything with this framework. So a neural network is just some big function, and hypothetically, if you chose it appropriately, you could approximate literally anything. Neural networks are so-called trained by updating. So the training of a neural network involves updating the parameters that appear inside it. For example, in the notation I've used here, the sets of W's and B's that appear in this concatenation, these are the parameters of the neural network. And in order to match your neural network to whatever function it is you actually want to approximate, you need a notion of a loss function. This is effectively a metric on parameter space that tells you how far away you are from wherever you wanted to be. So let's write this in this way, where yi's are where you want to be, and here's the functions that you're producing at the end. Supervised learning, and I'm oversimplifying dramatically here in many of these things, but let me be schematic for a moment. A common thing to write here would be, for example, the mean absolute percentage error. So something like the following. Which is just really, this is where I want to be, this is where I am, let's try and make this small, right? Can I minimize that error? How is that minimization done? This is an optimization problem that needs to be done step by step at each iteration. And a tool for that is to optimize via gradient descent. So what is that doing? In some sort of cartoon of the space of parameters, we're going to, if we consider this sort of topographic map here, the neural network starts somewhere, it adjusts its parameters, and it checks the gradient to see, just like you were walking down a hill, you want to say, am I going down or not? It goes down a little bit, it stops, it checks, and says, okay, where's the next place of steepest descent? Now you try and walk down the hill that way, and you're going to optimize your gradient descent down the hill by literally just taking a step, checking, am I going down? How fast am I going down at each little step as you move downward? Okay, so that is the super simplistic 2-second review of what neural networks do. So now what do I want to do in the Calabi-Yau context with this technology? Obviously, something like this as a loss function doesn't make any sense for me if, for example, I wanted to compute the Calabi-Yau metric because I don't know the Calabi-Yau metric that I want, okay? I can't compare to any known data set to train. But it turns out that exactly the same technology, and indeed the fact that these are just like any other series expansion, these are universal approximators. With the right loss function, you can literally just update the neural network step by step to optimize against a different loss. And the question is, what loss would you like to take? So let's look in the Calabi-Yau case for a moment. What do we want to know? Many things in my effective theory depend on the Calabi-Yau metric. For example, this matter field Kähler potential that I just alluded to that would be essential for computing normalized quark masses. That I need to know the metric in order to compute that Hodge star. So the question is, how do I set this up as a neural network problem? One guess might be to try and build a loss function that is some function of the curvature, right, et cetera. As it turns out, you can set that up that way. So you can just literally try, if you're looking for a Ricci flat solution, you can just try and minimize on curvature step by step in a neural network. That proves to be very slow because this is highly nonlinear and higher order. So this is not a great choice, as it turns out. Fortunately, though, the structure of Calabi-Yau manifolds actually gives you a very nice and natural loss function. So there is a Monge-Ampere type equation that I introduced on the first lecture, which said that J wedge J wedge J, where these are your Kähler forms on the manifold, are proportional to omega wedge omega bar. These are top forms, so each of these are 3-3 forms on the Calabi-Yau, and there is a unique such 3-3 form, so any two must be comparable to each other by an overall factor. As a result, if you want this to hold in the Calabi-Yau case, you can define a loss function based on this equation as the following. Now, why is this better than just directly optimizing on the curvature? As I will show. One quick aside, this equation, as you might recall, the fact that these two guys are proportional actually holds for SQ3 structure, not just in the Calabi-Yau case. So if I'm interested in the Calabi-Yau metric, what do I need to add in addition? I need to optimize on something like this, and I need to demand that J is Kähler. Specifically that DJ is 0. Right. So if I have a DJ that is 0, and then I impose this equation, I should be in the Calabi-Yau case if it's satisfied. The real reason that this is computationally nice is that for simple CYs, such as all of the ones I introduced in the last couple of lectures, so toric hypersurfaces, complete intersections in toric hypersurfaces, the form of the holomorphic 3 form is actually known explicitly. So this part of the input is fully specified. And moreover, let me give as an example, in the case that I have a single system of equations, Pi is 0 in CPN, this can be generalized, but let me just state it here in a simple way, then the actual Calabi-Yau Kähler form, you can show must be in the same class as the Fubini-Studi Kähler form, and can only differ by 2 derivatives of some Kähler potential. So the actual Kähler form you want is the same class as the Fubini-Studi one with a shift. This is very much related to that form of the restriction of the curvature that I mentioned in one of my lectures, where we argued that these hypersurfaces were indeed Calabi-Yau. All right, why is that now buying us something of use? Because now, if I plug this in here, if omega is effectively known for some algebraic description of the Calabi-Yau, and I want to parameterize J as the difference from the Fubini-Studi Kähler form, which I know, now I need to optimize on something second order in this phi, whereas if I were optimizing directly on the curvature, that would be fourth order in phi. So this is a substantial advancement in terms of how this works. Okay, so I'm going to omit many details in the interest of time, but let me just schematically say what one does. In order to actually make this your loss function, so here, by the way, I should say, this is really an integral over the Calabi-Yau in order for this to make sense. In order for this to be your loss function, you need to be able to numerically integrate on the CY manifold, which means that you need some explicit description of that manifold. This is a reason why people, in starting to do this, as I'll talk about in a moment, have focused on the Calabi-Yau case, or simple SU3 structures where you can really write an explicit manifold down. If you try and do this for some arbitrary manifold, you don't know how to even set up the loss function or integration problem because you need something to explicitly evaluate. So if you have that explicit description of a Calabi-Yau, you can numerically integrate over it. You can use points for both training and then points to determine the metric. And then this proximity to the Fubini-Studi metric, you have J Fubini-Studi and omega explicit. And there's actually some neat tools that were already developed in the numeric metric literature in terms of how to perturb the Fubini-Studi metric in a way that's very efficient in terms of the number of parameters that you want to start toggling and training. And this is to do with a broad program known as the Donaldson algorithm, which has a lot of nice mathematical results in terms of finiteness of fluctuation and how close you are and how many iterations you need to do to achieve certain accuracy and so on. So not going to talk about that all right now. But what can be done? So my group and others, collaborators.
Sorry, Lara, can I ask you a question?
Sure.
So, for instance, here you have to determine this function phi.
Mm-hmm.
So, do people use something like a lattice discretization of the manifold to construct this function, or what is the
No,
technique?
so in order to do the numeric integration, you do something like adaptive mesh integration. So you have to be able to algebraically set up the manifold, distribute points, have some notion of what your actual manifold is. But at the end of the day, the neural network itself is some function, right? So your description of phi is, something. But yeah, the sort of numerical element of it really comes into setting up this integration problem. Correct. But remember that the metric is Kähler, so you can write that as two derivatives of a Kähler function, and the claim is that this phi is going to, phi plus the Fubini-Studi is going to give you the actual Kähler potential you want.
Okay.
So yes, the goal was, so good, yeah, I just erased, so two different G's, sorry, I thought you were referring to metric GID. The matter field Kähler potential, yes, we want that. So that's actually what I'm about to talk about next. So let me just say what happened a few years ago. So starting in about 2020, myself and my collaborators, group led by Mike Douglas, various people started actually implementing this seriously with neural networks. I should emphasize that this obviously is not, like for me personally, machine learning and neural networks are not my primary focus of research, so there was no claim that we were writing the very best or most efficient neural networks. We were just trying this out as sort of a proof of principle. And there are many groups. I will flag in particular the group at Northeastern that has a whole center focused on machine learning and physics. There are many groups that are really thinking hard about how to, fully optimize neural networks for many problems in physics. But here was the punchline even for sort of initial explorations. I personally had been involved in numeric approximations, not using neural networks, but using things like this Donaldson algorithm many years ago. And the historic state of the art was that if you had to do a problem like this to approximate a metric, you would set up the numerics, you would run it on a supercomputer for a couple of months, and then you would get a metric at a point in moduli space. And then you're like, great, what do I do with it after that? It would just be this incredibly cumbersome process to produce a numeric metric that wasn't even a function of the moduli. So the big regime change with this is that these things work. You can produce metrics. Indeed, people have been exploring how they can make metrics as functions of both the Kähler and complex structure moduli explicitly. And they're upping the number of such moduli they can describe. And here's the really important part. It's really fast. So these computations run on a laptop in a matter of minutes, not on a cluster in a matter of months. So now you have questions that you can ask and then outputs that you can analyze much faster. What is it that you want to then do? And people indeed have in the last couple of years in a real tour de force of pushing these techniques forward. So what I just illustrated very schematically was a computation of G Calabi-Yau. So let's say we've done that numerically. Now we need to go away and solve the Hermitian Yang-Mills equations. So we have our GAB bar, FAB bar. Now we need to find the Yang-Mills connection. And then once we've done that, we need to consider bundle-valued harmonic forms, which were in this matter field Kähler potential that I just erased. So these are what I was referring to as V, I forget which index, VI, VA. These guys that appear inside the matter field Kähler potential, and the full GIJ matter field should then be computable. So there's an iteration of numeric things you've got to go after. But importantly, in the last 2 years, people have actually done this all the way through. And they have computed normalized quark masses. In one of these compactifications. Importantly, those quark masses are, quote, wrong. They're not the quark masses of the standard model. But the fact that you can actually write them down now as functions of moduli, you can actually push that 4D theory all the way through to that explicit endpoint is really cool, in my opinion. So this is a major step forward. Another thing that should be said at this point is that the nice thing about many of these tools is we applied them first in the Calabi-Yau case, but in my first paper on this subject, we also decided to explore whether we could go after the SU3 structure as well. And a really nice property of this is that using this Monge-Ampere equation, this didn't care whether I was Calabi-Yau or SU3 structure. So the basic form of the loss function you want to write down is really similar in the two cases. And you can ask, can I just efficiently push this all through in the SU3 structure case? The limitation, at least to my initial pass at this, is what manifold do you want to write down to now begin setting up this problem? So the difficulty with SU3 structure is that we don't have these theorems of sort of, here's these nice sets of algebraic complex manifolds where you can just, start to go to work in terms of what it is you want to compute. So as a first point of principle, we actually explored this, but we took sort of an easy class. And we asked, what happens if we wanted to build SU3 structure solutions over algebraic Calabi-Yaus, but now we're going to find solutions with flux that are not the Ricci-flat Calabi-Yau solution. So we're going to put different metrics on algebraic Calabi-Yaus. That's certainly not the most general case, but it's a nice starting one to try out this technology because, again, you have an explicit form for example, the holomorphic 3 form, and you have a space you can actually integrate over because you can just write it down. So SU3 structure, we still have the condition that J wedge J is 3i over 4 omega wedge omega bar. That still holds. You have a set of torsion classes that you need to specify in order to specify the solution. And so what we tried to do at first pass to test this out, we were a bit nervous because we have no Yau's theorem that tells us that a Ricci-flat metric exists, or whatever metric exists in this case. We were worried that we might get numeric relics that we couldn't control. So we wanted to have a known solution that we could target to see how well does the machine learning algorithm actually spit out the answer. So for that, we used a known solution over a Calabi-Yau hypersurface. Here I'm going to choose as the background manifold the quintic again as the simplest possible thing. I'll write J as a sum, I equals 1 to H11. Ji, omega as its some real and imaginary parts, these coefficients real, and these ones complex. And then importantly, you can find SU3 structure solutions with the following form. A1 in this case of the quintic, H11 is only 1. A1 squared, A2 is 0, and go back down over here. Sorry to do this in two different places, but where here sigma is just the sum A equals 0 to 4 of the coordinates on the quintic. And in this case, this leads to torsion classes. W1, W2, W3 is 0. W5 is 2, W4. And this is equal to 2 d ln of A1. Okay. This is not crucially important, except to say that there is a very explicit SU3 structure solution that we can now just fully write down. And so our question was, if we knew this solution existed, can we train a neural network to find it without imposing this final structure? We're going to impose the Monge-Ampere condition. Because we had dropped K-larity in the SU3 structure, you can no longer explicitly build your J your two form as a Kähler thing. Instead, you have to use sort of the innate properties in terms of underlying torsion classes, and we had to put together overlap conditions explicitly to make sure our manifold made sense as SU3 structure that weren't guaranteed in the case that you have a non-Kähler manifold. So importantly, what we found is that the neural networks converge to the known solution. And that SU3 structure is equally easy to, let's say structure here, to SU3 holonomy or Calabi-Yau case. So from the point of view of the neural network and the optimization problem you're doing, there was really no difference in efficiency or accuracy between SU3 structure and Calabi-Yau, which again is neat because we had no analytic tools for attacking the SU3 structure solutions in many cases. Here we tried it out on sort of a dumb toy example. How would you go after this for more general SU3 structure manifolds if you want to compute? The basic setup works, but you need which space explicitly you want to be setting up the numeric integration problem over. And as one in to try and do that quite generally, we're going to appeal once again to Reed's fantasy, which I introduced in the notion of geometric transitions, which is the belief that all of these spaces, SU3 structure, are connected by geometric transitions. So we are interested now, and this is work in progress with collaborators, we're interested in trying to explore if we have a geometric transition between X Calabi-Yau and X SU3 structure, which destroys the Kählerity condition, can we set up a machine learning problem in order to find that SU3 structure metric and solution using the basic algebraic space of the Calabi-Yau and then tracking how it begins to break the Kählerity condition upon, for example, small resolution. So we want to bootstrap what we understand about how to explicitly write down those explicit Calabi-Yau backgrounds and then modify the metrics now locally around these resolutions. So this is work in progress. Okay. Any questions on the machine learning thing? Because I'm about to go somewhere different. Yep.
Yeah, so initially when you were discussing this, you had this vector bundle, right? I mean, and you said that, I mean, it breaks some symmetry in the E8. Basically, probably this gauge field's getting some Vev.
Correct. Gauge fields over the Calabi-Yau, having Vev in background breaks the 10D symmetry down to something in 4.
Where exactly are those going in here, or like?
Right. So I did not explicitly show you that. So here I've just talked about the metrics. That was the sketch of computation that I mentioned here. So once you have the metric, then you use that metric to, again, numerically solve this equation.
Okay.
So find the gauge connection on that vector bundle that satisfies Hermitian Yang-Mills. Then you go away and find vector bundle valued harmonic forms. So you have to solve the harmonicity conditions, which are metric dependent. They involve a Hodge star for things that live in that bundle. So in my initial work on this, we didn't actually push this all the way through, but in recent years, people have done that. So there was known numeric literature on how to approximate these gauge connections that I also worked on many years ago. So this was sort of understood, once you have the metric, what you would want to do to numerically compute that. And then the new thing was actually solving these harmonic forms and getting the matter field Kähler potential. And that was only done in the last, year and a half, 2 years.
Okay. And one more thing, like this loss function that you wrote, you said that it's an integral over the Calabi-Yau.
Correct.
Is there an analog of this for non-compact Calabi-Yaus that Marcos has been discussing this?
I would have to think about that further. It would depend on what the problem was you were trying to set up. So would the question be, can you write down metrics on the non-compact Calabi-Yaus?
But I guess those are already there.
The Monge-Ampere equation, no, will not hold in the non-compact setting. But whether there are other similar constraints you could write down, I personally haven't thought about that, but I bet other people have. So, I think locally. In the non-compact setting? Okay.
I have a question. What is your input of of your neural network. And if there is many degeneracy about your input, how do you handle this case like many to one map in your dataset?
Right. So there are many parts of the input. So points over the Calabi-Yau. Also, we can input parameters in sort of known starting points of the Fubini studi metric. So for example, I haven't talked about this in detail, but in the Donaldson algorithm, it basically provides you with a set of tunable parameters in a generalized Fubini studi metric that are guaranteed under certain tweaks to converge towards the Calabi-Yau limit eventually. So one way that people have set this up, among many, is to actually use like inputs of the Donaldson algorithm as part of your input that you're then, the neural network is optimizing for you as the output. But yeah, happy to talk offline about more detail of that setup. Okay, so for my last couple of minutes, I want to pivot now. So I wanted to give you a flavor of where there has been interesting progress. The numerics are certainly a big step forward in recent years, and one that lots of people, myself included, are paying attention to. There also has been a lot of formal understanding about the structure of these moduli spaces, and I have mentioned this already, but perhaps redundancies in these moduli spaces that may make it more efficient to try and extract the low-energy physics or to bound and characterize these geometries. So in the last 10 minutes, let me just give you a brief flavor of what some of those structures look like. So first, I need to talk about the n equals 1 moduli space. That could be the full moduli space of singlets, including, all of the degrees of freedom in the theory, the, Calabi-Yau moduli, the dilaton, the bundle moduli. Let me do this sort of stepwise, and I'm going to consider the holomorphic moduli first. So holomorphic moduli of the theory are H21 of the Calabi-Yau and H1 of the bundle. These are the so-called bundle moduli, fluctuations of the gauge connection, which satisfy Hermitian Yang-Mills. These each arise mathematically as the first order tangent spaces in a general deformation problem. Specifically, these are the first order deformations of X as a complex manifold. Okay. These, what are normally called the bundle moduli, are the first order deformations of the bundle. So these are what would be referred to as def V, holding the complex structure of the base fixed. Okay. So geometrically, these problems and deformation spaces were set up very, straightforwardly by geometers in the 1950s, people like Atiyah and Spencer, so on. So these spaces are understood, but neither of those is actually the right one to correspond to fluctuations of, the flat directions and the potential of the heterotic theory. There you want to let all fields vary simultaneously. Okay. Fortunately, at least in the holomorphic sector, this actually does correspond to a deformation geometric problem that was also studied by geometers, and this is the simultaneous deformation space of a vector bundle and its base. This was studied in great detail in the 1950s by Atiyah in particular. And importantly, the first order deformations of this space are not the sum of these two. They're a more complicated mixing of the two. So in brief, what you can show is that the first order deformation space, I'll call it H1Q, and there can indeed be obstructions in this space, so it's not guaranteed to be unobstructed, but to first order, I'll refer to them as H1Q, where this is defined by the following short exact sequence. I'll call this pi. This is a short exact sequence. If you write this down, you can ask, what is Q? Q is actually, if you write the following, so let me define Z as the projectivization of the total space of the bundle. So if I consider the non-compact vector space fibers of this bundle point by point over the geometry, I compactify those fibers to write some really huge compact manifold. If you consider the complex fluctuations of that, these would be H1 of TZ. And if you consider the projection of those to the Calabi-Yau, you can show that Q is the projection, I need a different name for that projection, we'll call it sigma star TZ. So this is the push forward to the base of the natural complex deformations of the total space of the bundle. As I mentioned, these are not a direct summation, so you can show, let me write this just briefly. You can show that equations like this hold. So basically what happens is you have a mix of two things where this guy right here is a complex structure modulus of the base, and this is a fluctuation of, a gauge field delta A. And the picture is, if you were considering only the base geometry, you would consider, all possible fluctuations of the complex structure that keep it a complex manifold. And under that condition, the holomorphicity condition would say that your fluctuations of your gauge field have to keep F02 and F200, and so this would vanish. But if you're willing to fluctuate both simultaneously, it can be the case that you can consider non-holomorphic fluctuations of your bundle that will become holomorphic in the new direction as you deform, or vice versa, there can be certain directions in complex structure fluctuation where the bundle can fail to adjust. Importantly, what this ends up doing is actually reducing the dimension of the total moduli space that you need to consider. So it is not the case that every possible bundle deformation and complex structure deformation of the base separately are in play. They talk to each other in non-trivial ways. And many bundles can effectively freeze out the complex structure moduli of their base manifolds. So without going into huge details, the resulting moduli space, so the dimension of H1 of Q is less in general than the sum of H21x plus H11 and 0v. And in many cases, you can choose, for example, the best that I personally have seen, although I don't have a theorem that this is the best you can do, you could choose V on X to effectively freeze or constrain H21 all but one. How do I want to phrase this? All but one, so I guess H21 minus 1 complex structure. No, it's the wrong way around. All but one. So to leave a single complex structure moduli unconstrained. When we initially started studying this, we were interested if you could find bundles to completely rigidify the base manifold, and I personally have never been able to find any of those, despite some trying, but I don't have a theorem that they don't exist. Okay, so you have this complicated moduli space. Who cares? What do you want to do with it? The question we now want to ask is analogs of things like mirror symmetry in the n=2 context. We want to ask about redundancy in the space of effective theories, and we want to ask about maps from moduli spaces like this that now combine these n=1 ingredients with the Calabi-Yau metric and ask, can we see nice symmetries in that space? Can we find nice mappings between such spaces?
And sorry, I have a question.
Sure.
Maybe you alluded to it. So these are first-order deformations. Is it known that these are integrable, or there could be obstruction?
They certainly are not in general. So for the n=1 moduli space, you can see this physically in that you have this big superpotential, right? That in general will just not, it's going to lift a bunch of directions. So unlike in the n=2 context where, everything's determined by the prepotential and you have no obstructed deformations, that maps deformation theoretically onto the Tian-Todorov theorem of unobstructed Calabi-Yau deformations. In the n=1 context, no. In general, things will be obstructed. So the first order deformations will be lifted, sometimes entirely. But there's a really neat result that I don't have time to talk about, which is that you can actually prove the deformation theoretic problem order by order is exactly the same as the 4D superpotential computation. So if you see a geometric obstruction, it will 100% be visible in the obstruction of the 4D theory and vice versa. So the geometry and the field theory are in complete alignment in terms of what that obstruction looks like. Okay. Cool. So last comment, and then I really am done. What have we noticed recently? We have found detailed studies about the properties of this moduli space and how to map it. And we have found many examples of geometries, which we've been studying explicitly. This has been a program that I particularly have been interested in the last number of years, for which you find pairs of vector bundles and manifolds. These are totally different manifolds, topologically distinct manifolds and bundles, such that the 4D EFT is, quote, the same. Okay. What do I mean by that? First off, that the massless spectrum is exactly the same at sort of leading order in the theory. So massless spectrum, both charged and uncharged. The massless spectrum agrees. The deformation theoretic problem that we were just discussing, so these obstructions that can arise beyond first order, the deformation theoretic obstructions, or let's say the form of, yeah, I'll just say obstructions, also can be shown to agree. And a very related computation, you can actually compute the holomorphic Yukawa couplings as functions of all the complex fields, and this is in general tens of thousands of functions. These also agree. So you end up with theories which really look like they should be the same effective physics, and you can ask, what is the structure of how this works? I could give a whole different set of lectures in terms of the dynamics of, what might happen in terms of connecting these two, how do you map the moduli spaces? That's not the thing I want to convey to you here. But one thing that we have introduced that you will appreciate is you can ask, just structurally, before I get into the physics, what classes of things will do this? And the examples that we found all have the following cool property. These are all examples where x and x tilde are connected by geometric transitions. Specifically, the ones we've studied so far are conifolds. So these are the same geometric transitions that played a big role in all the classifications I was talking about over the last couple of days. But now what we're seeing is that there appear to be things that are morally flat directions in the effective theory, where in the presence of gauge fields, your Calabi-Yau manifold is going singular, but the complete n equals 1 theory allows you to sort of traverse that singularity in terms of keeping the effective physics the same, moving across these geometric transitions. So the actual physics at the singularity points is extremely complicated. We don't have a complete story for that yet. But at a practical level, what we found is how to take a v to a v tilde that can adjust perfectly for the conifold transition. So if your base is changing, we figured out rules for how to change the gauge fields over them such that the physics stays the same at the end. There's a lot of interesting questions about what kind of duality would this be, how do you map the moduli space? We could talk about that. But at a practical level, what that tells you is that if you were interested in scanning for physics, let me do my schematic Kreutzer-Skarka diagram again, right? You have all these Calabi-Yaus and lots of points moving up in H11. What we are showing is that there is an embedding of bundle moduli spaces from low H11 to high. So you can embed moduli spaces of B from H11 low to H11 high. And instead of a dual pair of theories, as I illustrated here, these are not actually pairs, they're chains that wind their way up this diagram. So there can be chains of 10s, 20, 30 manifolds and bundle pairs in what we've explored so far that move upwards across these conifold transitions, some that can go much further. Why is this relevant? Because again, it tells us that these geometric transitions are playing a really strong role in terms of bounding and classifying what geometries can arise. And also, if you're just practically interested in terms of what physics you can get out of these theories, it's not the case that you have to check all 500 million and then every possible bundle over them. There's a stratification of that moduli space moving upward in this diagram that you can carry forward in powerful ways. So I am going to stop here because we have to move to the discussion session, but I hope I've given you a flavor, a little bit of some of the background geometry that goes into these calculations, and also why at least still progress is being made in the subject of string compactifications. So I'll stop there and we can chat.
Thanks a lot, Lara, for the series of lectures. Questions?
Hi, so I have a question about this constraint you said, like, on one hand, it's like a vector bundle deformation, and on the other hand, it's the complex structure deformation, and those are sort of related. Can you give us very simple example where this happens? Like,
absolutely, yeah.
Yeah.
So that was something, formally you can write down this geometry, but for me, I don't feel like I really understood it until you can just write down some explicit bundle and then be like, how does that happen? The easiest way to make that happen is to try and build a bundle and to make the ingredient you need to build the bundle dependent on the complex structure in a really obvious way. So it's a way to sort of bake in something that's going to do this explicitly and then, see that it works the way you expect. So there are lots of ways to do that. Let me give just one really dumb example. Let's work our way upward in complexity. So first question you could ask is, could that obstruction ever exist for 1 billion gauge fields on a Calabi-Yau? That's pretty easy to show, no. 1 billion gauge fields are just, they're defined as, by line bundle divisor duality. They just exist for the manifold. No obstructions can exist. For every complex structure, they're fine. But now let's try and make almost the next simplest thing. Let's consider the following extension of 2 line bundles. So this is a short exact sequence. There could be some non-trivial X group, X1, L dual L, which in this case, if these were line bundles, would be something like this. So this is something that is almost the direct sum of these two, but non-trivially mixed together. So if you were to write the gauge connection A on V schematically, this looks like, A on L, A on L dual, and then this X is the non-zero part that, is mixing the two together. So it's a non-abelian, in this case, SU2 bundle that you could build simply by, choosing to turn on these deformations that glue these 2 line bundles together. This is, again, super easy construction, so you can write that down. It is very easy to find line bundle cohomology over Calabi-Yaus, which jumps at higher codimensional loci in complex structure. So what you do is you say, I want to choose a line bundle for which this X group will actually only exist at a higher codimensional locus. Then that is the only place you can build that bundle, and you might expect, deformation theoretically, that the theory is going to protect itself and it's going to freeze you to those complex structure moduli that keep that key ingredient in play. And that is indeed how it works. So this is sort of the easiest possible example to study. It happens much more generally, but this is something that's super explicit, because if you just want to say, for some line bundle cohomology, when does this have a global section, when it doesn't, that's a commutative algebra problem you can just solve.
Okay. And one more thing about this, you said that the massless spectrum is same for the resolved and the deformed side.
Mm-hmm.
Yeah. This doesn't happen in the Chern-Simons case theory and the topological. That example, probably this doesn't happen, right? I mean.
So this is very much not ordinary mirror symmetry. So this is actually a question that we were interested in for studying this. If you took, for example, the holomorphic tangent bundle on this side, so you're enhancing the world sheet supersymmetry from 0,2 to 2,2 at that locus, you can ask, do I move to like a 2,2 point on the other side? And the answer is no. So if you started with something, near the standard embedding, or that, you might hope to inherit normal Calabi-Yau mirror symmetry, what you get does not look like the other side. So it's really n equals 1. It's not inherited from n equals 2. So yeah, no A or B model here because we're not in the n equals 2 context.
Okay. And one more thing. In the beginning you said that you'll discuss D-branes also, but
I didn't get there. Yes. So what can be said about that? So it turns out actually this whole, I'm only giving you, the teaser trailer here, but the basic ingredients of why this happens, we discovered are actually, I erased it already, but what the dynamics across the small instanton transition are in the heterotic case that actually cause these bundles to be the same, to have the same spectrum, actually arise crucially from a property of NS5 branes across conifolds. So we showed that we can basically come up with NS5 branes that will compensate for the conifold in a very explicit way. And then through small instanton transitions, if you absorb them into bundles, these are the class of bundles that will behave. Once we understood how to do that for NS5 branes, you can then just say, can I do it for other branes? So we've also looked at this in the case of 2B orientifolds, and we can construct examples there, again, that have all the same properties of the theory we can construct. You can do it for type 1 theories, right? So any other theories where you have sort of appropriate, dimensionalities of branes you can write down. You can ask if there's analogs in F theory for Calabi-Yau fourfolds, and there are. So there's a whole more general story about, I would say the takeaway message is how the n equals 1 ingredients play with geometric transitions, whether that's fluxes, orientifolds, branes, and so on, bundles in this case. And the answer is they can do a lot.
Okay. Like, I have a more specific question about D-branes. Like, if I want, suppose a D-brane wraps some cycle in the Calabi-Yau, and I want the open string spectrum for it. Generally, I think it's a very hard problem unless you have,
Correct.
I don't know, some symmetry or some CFT, description of it. But can this ML techniques make it possible, or like, is there work in that direction?
I mean, in general, I don't have a claim about that. I mean, a related question to what you're asking is, to really understand this, what I would love to do is to be able to say what happens at the geometric singularity in this context, right? So in practice, I can build these geometric pairs that are going to give me the same answer. I can sort of understand at the level of geometry how to modify the bundle to make it compensate for the conifold. But what I'd really like to see is in the n=1 theory, as I move to that locus and moduli space where a cycle is collapsing to 0, I should be getting a bunch of extra light states in that theory due to branes wrapping that cycle. And if this is a smooth transition, I need to show why why those extra light states get lifted, or why I dodge a singularity. Why is the physics the same? I don't know how to do that computation in the n=1 context at those singular limits yet. There are very few tools for that I'm aware of, but.
Okay.
But I think it's a great question. So yes, in the n=1 context, being able to compute spectrums of D-branes at singular limits, very important. Don't know how to do it.
More questions?
Hi. So if I remember right, there are in symplectic geometry some metric compatibility relations that relate the Kähler form, complex structure, and the metric. So can one not use these to try to infer the metric on Calabi-Yau manifolds?
Are you saying analytically or in the machine learning context?
Either, I guess.
Yes. There are indeed these conditions. These are not sufficient analytically to determine the Calabi-Yau metric. Whether you could come up with more clever ways of phrasing the numeric problem, hypothetically, yes. By no means do I claim that what we've done is the only or most efficient way of numerically approximating. So this is something we explored a little bit in these numeric approximations, was sort of which constraints get you where you want to go faster, right? So we tried sort of setting up general constraints on Kählerity, on Monge-Ampere, on overlaps. We set up all these different things, and then we tried turning them off one by one, right? So, do you see like which ones are actually driving convergence of these solutions? What's most important for the neural network? Could there be other, symplectic geometry conditions you could impose that would make them better? Sure. But yeah, we have not fully answered that question.
Maybe unrelatedly, you mentioned how n=1 and n=2 differ as for the flat directions in the superpotential. Mm-hmm. Can you elaborate on this? It's not really familiar.
Sure. So that was very brief, but this has to do with your notions of geometric and physical moduli spaces. So let me take the n=2 context, just like type 2A, type 2B on a Calabi-Yau. A Calabi-Yau has a natural moduli space, as a geometer would describe it, in terms of metric fluctuations that are going to preserve your Calabi-Yau condition. You can ask, as we were just doing, things like H1Tx, which is H21 of the Calabi-Yau. These are the complex fluctuations of the manifold. You can ask, where does this space arise in the deformation theoretic problem? These are fluctuations delta G that keep your manifold complex to first order. Okay? Not necessarily to higher order, so it's a linear fluctuation analysis that tells you this is the right thing to consider for a Calabi-Yau. Now you can ask, if I were to do it to all orders, what would happen? And this was studied by mathematicians. This is a theorem by Tian and Todorov. And they showed that order by order, if you were to keep, first order fluctuations, second order, nth order, that the first order fluctuations are never obstructed. So the first order answer is the whole answer. So this tells you that the Calabi-Yau moduli space, and this underlies the special Kähler geometry and, hyperkähler geometry, all this cool stuff that we use in the n=2 context. It tells you these moduli spaces are true moduli spaces, and you have a real complete understanding of what those deformation theoretic objects are. That corresponds in the n=2 language to the fact that the entire potential is determined by a prepotential. So there's sort of an innate structure of the n=2 theory, and the fact that the moduli space is going to be, hyperkähler and nice, that is a function of the large degree of supersymmetry that tells you, again, this moduli space from an effective field theory point of view, if you just do a fluctuation, in vacuum, the zeroth order flat directions first order flat directions will be higher order as well. You will not lift you won't have potentials that start small and then lift up somewhere, right? So you're not going to be fooled if you think that's a first order flat direction, but then it's really not. In the n=1 context, totally not true. So both geometrically and field theoretically, you can write down an effective theory, and to first order, you can fluctuate it and say, what is the zero locus of my potential? And that can be there, and then there can be higher order things that lift. Order, I'm not talking here about alpha prime or, string expansions, I'm talking about just order by order in the field theory. So first order fluctuations in general are obstructed, and this arises in n=1 theories by the fact that the structure of the potential is different. It's determined by D and F terms of the superpotential. And so there's just a lot of functional freedom to make more complicated potentials.
Thank you.
If there's no further questions, I just wanted to say thank you guys very much. It has been a pleasure talking to everybody. I've had lots of really interesting conversations, and I was very impressed with all the students of this school. So, thank you.
Thank you.